Many people view air conditioning as a process of manufacturing cold air and blowing it indoors. However, cold is not a physical substance that can be created. In physics, cold is defined as the absence of thermal energy. To make a space feel colder, the system must extract the heat already present in the air and move it elsewhere. This extraction must overcome the second law of thermodynamics, which states heat naturally flows from high temperature to low temperature reservoirs. Cooling a building requires forcing that thermal energy in the opposite direction, pulling heat from a 22-degree interior and rejecting it into a 35-degree exterior. Moving energy against this natural gradient requires the machine sitting outside your house to function as a thermodynamic heat pump. Reversing the natural thermal flow requires a closed-loop mechanical architecture. The system uses pressure manipulation and phase change chemistry to transport heat toward the hotter outdoor environment. The system relies on a working fluid called a refrigerant, such as R32. This chemical is chosen for its ability to change between liquid and gas states at relatively low temperatures. The cycle begins at the indoor unit's evaporator coil, a network of copper or aluminum tubes located inside the building. An indoor fan draws warm air from the room and pushes it across the metal fins of the coil. Inside these tubes, the cold liquid refrigerant absorbs thermal energy from the passing air. In this cross-section, you can see the fluid boiling and transitioning into a low-pressure gas as it takes on that heat. Because the evaporator coil is significantly colder than the room air, moisture condenses on the coil's surface, providing the secondary benefit of dehumidification. At this stage, the indoor unit has successfully captured the room's thermal energy into the refrigerant vapor for transport. This low-pressure, heat-laden gas travels through an insulated suction line to the outdoor unit. It enters the compressor, the most energy-intensive component in the entire loop. The system now utilizes Gay-Lussac's law, which defines the direct proportional relationship between a gas's pressure and its temperature. By forcefully squeezing the refrigerant gas into a much smaller volume, the compressor causes its pressure and temperature to rise simultaneously. The resulting high-pressure gas is significantly hotter than the summer air outside, often reaching temperatures between 60 and 80 degrees Celsius. We expend electrical energy to spike the refrigerant's temperature above that of the outdoor environment. This allows the captured heat to finally flow outward into the hot air. The superheated pressurized gas enters the outdoor unit's condenser coil. A large propeller fan pulls ambient outdoor air across the condenser fins. As shown in this cross-section, the refrigerant gas is hotter than the outside air, so it rejects its stored heat to the environment. As it cools, it transitions back into a high-pressure liquid state. This liquid leaves the condenser and travels to the expansion valve. The expansion valve acts as a mechanical choke. As the liquid is forced through a tiny opening, its pressure drops instantly, causing the temperature to plummet. This rapid expansion resets the fluid to a cold, low-pressure state. It is now ready to return to the indoor evaporator coil and repeat the heat removal cycle. Beyond the mechanical plumbing, modern systems rely on advanced power electronics to manage the compressor's energy consumption. Traditional non-inverter systems run on fixed-frequency AC power. This means the compressor is either operating at 100% capacity or is completely shut off, which creates massive current spikes and temperature fluctuations. High-efficiency systems instead use an inverter board mounted in the outdoor unit. This process begins with rectification. As the graph shows, the incoming alternating current is converted into a flat DC line. The circuit then inverts that DC power back into an AC wave. Crucially, the system can now dynamically alter the frequency of that wave. This variable frequency allows the system to throttle the compressor motor speed precisely. The compressor can ramp up for rapid cooling or slow down to maintain a room's temperature using minimal power. Eliminating the start-stop cycle prevents electrical current surges and reduces mechanical wear. This continuous variable operation increases energy efficiency by 30 to 50% compared to fixed speed models. Viewing the entire split system reveals a sophisticated interaction between indoor extraction and outdoor rejection. The four pillars, evaporation, compression, condensation, and expansion, form a continuous loop modulated by inverter controls. This distributed design is a significant departure from the all-in-one window units of previous decades, such as the one shown here. On a macro scale, these systems represent a massive portion of the peak electricity demand placed on global power grids. Because of this scale, the industry is transitioning to refrigerants like R32. As this chart demonstrates, modern refrigerants have 1/3 the global warming potential of legacy chemicals like R410A. Modern indoor comfort relies on the precise application of fluid dynamics and electromechanics to manage the movement of thermal energy.